Welcome back. Today we're going to talk about managing option portfolios. Specifically, we're going to talk about different exposures you may have when you hold a portfolio of options. We're going to talk about the so-called Greeks. We're going to develop some mathematical intuition behind what each Greek actually represents, starting from the basic idea of a linear approximation. If you have no mathematical background, then we're going to do this visually so it makes sense. And then we will apply it to the idea of an option contract priced via the Black-Scholes model. And we'll talk about hedging and the idea of hedging our different risk exposures using a portfolio of options and or stock. Let's begin by discussing this idea of a linear approximation. We're going to talk about a first-order Taylor series approximation of this polynomial function f of x, and though the mathematics may sound difficult to comprehend and it may sound relatively rigorous, it's actually quite easy to interpret once we get to the visual component of this, so bear with me here. What we have is this idea of an approximation of a function. Now this function could be an option pricing function, it could be a profit function, a cost function. The actual interpretation of the function doesn't matter. You can still apply this Taylor series expansion approximation. So what we have here is we have this function is approximately equal to the function evaluated at a point of interest. This point of interest could be the current market prices, the current market parameter set. It could be the parameter set yielding the profit of last year. It could be the parameter set yielding the costs of last year. You can use any point of interest to develop this idea of a linear approximation. So it's going to be the function evaluated at that point of interest plus the first derivative of the function. Again, that function is the pricing function, the profit or cost function, whatever it may be. The first derivative of that function evaluated at that point of interest times a new point of interest less the point of interest. So we have this idea of x0 being the initial point, the starting point. That could be the current market parameter set, could be a parameter set from last year. Then we are trying to figure out, hey, what does it look like at this new point of interest, that is this x, okay? So what about this derivative here? What if we don't know how to compute the derivative of this function? What if it's got an intractable analytical solution? Well, check out my video on why the definition of a derivative is useful, and you can actually develop an approximation for this overall approximation. So you can approximate this derivative, then you can approximate this overall functional approximation. So that's enough mathematics. Let's talk about the intuition behind a linear approximation. All this fancy terminology aside, a linear approximation, linear means line. We are using a line to approximate a function. We have a nonlinear function here in blue, that is this polynomial x squared. And as you can see, the nonlinear function is being approximated at a point of interest, and that point of interest in this case is 10. And I've created this slider to show you what happens as you change the point of interest. And what you'll notice is the approximation tends to be very good about the point of interest. So we're actually using a linear function to approximate a non-linear function. That's this idea of a linear approximation. And this is only a first order approximation, so the approximation can get better. But let's just focus on this idea of a first order approximation. As you can see, if I go a little bit to the right of the point 10 or a little bit to the left of the point 10, that is our point of interest. That's our x0. As I said, it could be the market parameter set or a parameter set for profit or cost last year. The line, the linear approximation, does a very good job approximating the nonlinear function, that is this x squared. But what you'll notice is because it is a linear approximation, it doesn't capture the growth of the polynomial. That is, as we move further away in either direction, the approximation gets worse and worse. And this makes sense, right? If I gave you information about this point 10, and I'm saying, hey, we're going to reduce the order of this polynomial, the further we get away, this distance between the red line, the linear approximation, and the nonlinear function is going to increase. This distance is the error. So as we get further away from the point of interest, the error is going to increase. That is the idea of a linear approximation. We can use this idea to very simply interpret how we can expect the nonlinear function to change when there is a change in the input. So a unit change in the input, what can we expect the overall function to change? So for example, if I have a unit change in the input of a pricing function, how can I expect the price to change? If I have a unit change in the input of a profit function, how can I expect the profit to change? If I have a unit change in the function or a cost function, how can I expect the costs to change? So that's why this idea of a linear approximation is so useful. It's very, very easy to interpret. Essentially, I'm saying is, hey, we have all these inputs. We have a function that describes price, cost, profit. When I have a very small change or a unit change in the input, what happens to the overall function? Does the price increase? Does the profit increase? Does the cost increase? Do they decrease? That is the idea of a linear approximation. So you can see here, if we move to the right, the line is increasing, and so is our nonlinear function. So we expect a unit change in x to yield an increase in this polynomial function. Same thing if we step to the other direction. We expect this polynomial function to decrease, and that's exactly what happens. Now, what about when we get to this new point? We're going to want to do another linear approximation. So let's say we start at 10. What happens if I step to the left 1? Well, we're going to expect the polynomial to decrease. Now I'm going to recompute this linear approximation for 9. And we can continue and do this in a iterative fashion. So we're going to continue to recompute this linear approximation. So as we move about the space of this function, our linear approximation is going to be centered about the point of interest that could reflect the current market conditions, could reflect the current inputs into our profit function or cost function, so on and so forth. So the idea of this linear approximation is it's very easy to interpret in the sense that we can say what happens to the overall function based on a unit change in a particular input. And it turns out if you have a variety of inputs, this makes it very easy to determine, hey, if I change this one variable a little bit and I hold everything else constant, what can I expect that function to do? So if profit is a function of, let's say, overall labor and overall materials, then what happens if I increase materials? What happens when I increase labor? We can see what happens to the corresponding profit function. Taking a look at actual numbers, we have this linear approximation about the point 10. How good is this approximation? Well, we're going to start at this point of interest 10. Let's move 0.1 to the right. What I'm going to do is I'm going to use this linear approximation and I'm going to use the actual function. So I'm going to use both the actual functional change, which is represented by a change in the nonlinear function, this polynomial function, and I'm going to represent the change in the linear approximation. Then we're going to take a look at the error. So what I do here is I have the actual function change and I have the approximate function change. And as you can see, the actual function change is 2.00 or 2.01 approximately. And the approximate function change is 2.0. That is a very good approximation. Now you can do a whole bunch of analysis that's going to tell you the actual interpretation and bounds of this error. But for what we're trying to use it for, this is a phenomenal approximation based on the intuition that, hey, when there's a small change in this variable x, how do we expect the overall function x squared to change? Clearly, when we move away from this point too much, this error is going to be significantly larger. Let's give an example. As you can see, we're moving 0.1 to the right. What happens if we move 5 to the right? We have quite a significant difference in the actual function change and the approximate function change. Moreover, if I move 10, you can see that this error is going to continue to increase. And that makes sense because this polynomial is growing at a much faster rate. Again, this is x squared versus just a linear approximation of that function. As we move away from this initial point, this distance, you can already see it here locally. As this distance as you move away from the point of interest, x0, the distance between the red line and the blue line is going to continue to increase, and that's what we can see here. You can see that if the change is 10, and we're centered at point 10, then the approximate change is starting to get significantly worse. If I make this now 20, it's getting even worse. If I make this now 50, it's getting even worse, and that's exactly what we see in our chart here locally. We can see as we deviate too much away from this point of interest, x0, the linear approximation gets worse. So what can we do? Well, just like with this slider, we can just compute a new linear approximation at the next point of interest. And that's going to give us the same intuition and interpretation of what happens to the polynomial function. Again, that could be the pricing function, profit or cost function, when there is a unit change in one of the inputs, in this case, x. All right, now that's a lot of calculus, but why are we talking about linear approximations anyway? Remember, we're trying to get at this idea of managing an option portfolio. And in order to manage an option portfolio, we need to understand the exposures that accompany an option contract. And in this case, we typically refer to them as the Greeks. That is a European call or put option based on the Black-Scholes model is going to have a variety of inputs that affect its price. We have the idea of the underlying stock price and the underlying stock price changing, the time to maturity and time to maturity changing, volatility and the volatility changing, the idea of rho and interest rates changing. And there are a whole bunch of not just first order sensitivities, but also second order sensitivities that you can compute. But you'll notice that there is no sensitivity to the strike price, and that's because it is fixed throughout the life of the option contract. So here we have our Black-Scholes pricing model. This is a nonlinear function just like our x squared. So if we have a nonlinear function just like our x squared, we can apply the same idea of a first order Taylor series expansion. In this case, we're just going to compute the partial derivative relative to the function, that is the Black-Scholes pricing model, for each of the inputs. And then we're going to have a linear approximation. Essentially, the way that you can think about it is we are going to have this pricing function and a red line for each of the inputs. So we'll have a linear approximation for the change in the underlying stock price, a linear approximation for the change in time, linear approximation for the change in volatility, linear approximation for the change in interest rates. And what we're going to be able to do then is analyze how we can expect our option value to change when there's a unit change in each of these inputs. So delta, these are the Greeks now, that is this idea of a linear approximation of the change in option price. We have delta, which is the Greek representing the first order sensitivity of the underlying asset price. We have theta, which is the same thing for the time to maturity. Vega, which is the same thing for volatility. Rho, which is the sensitivity to interest rates. And then gamma is a second order sensitivity, but we're not going to focus too much on that. That is the rate in which delta changes. That's going to be a video for another day. But essentially, all of these Greeks are just using this idea of a linear approximation. What we're essentially doing is we are doing this linear approximation for each input into the Black-Scholes model. So there are 4 inputs into this Black-Scholes model to determine a price. Of course, there's the strike price, but that's fixed. Okay, so I know there are 5 inputs, but bear with me. The strike price is fixed. These 4 inputs can change throughout the life of the option contract. So what we're going to do is we're going to compute a linear approximation for each of these inputs, and then we're going to be able to see at any point in time how we can expect our option contract or our portfolio of options to change when there is a change in one of these input variables. And keep in mind, the underlying asset price changes all the time. The time to maturity changes every day. Volatility changes every day. It's a continuous process, right? Implied volatility, even though the model assumes it's fixed, it's not in reality, right? Volatility and the implied volatility of an option is determined by an equilibrium price and backing out the volatility to produce that market price. So these linear approximations are going to give us insight into how we can expect our option portfolio to change when any one of these variables change. How is this useful? Well, if we have no idea how our option portfolio is going to change when there's a change in the underlying asset price or there's a change in time or change in volatility, then how can we possibly understand our exposure? If all of a sudden there's a massive amount of uncertainty due to tariffs or macro changes or whatever this is, maybe fear starts to increase and volatility increases. You should know what happens to your option portfolio if you're net positive or negative vega, if your portfolio value is going to increase or decrease. That's exactly what this linear approximation is going to tell you. That's exactly what the Greeks are going to tell you. So I've built functions here for each of the Greeks that we are going to analyze. That is these four: delta, theta, vega, and rho. And I've also developed a pricing function for the Black-Scholes call. I'm going to post this. I'm going to link it in the description below. I'll post it on GitHub if you want to check out this Jupyter notebook. What I have here now is an example of delta, theta, vega, and rho relative to a parameter set for one European call option. So what I have here is I have the current market parameters. I have the current underlying asset price, the current strike price. Remember, this is fixed throughout the life of the contract, so there is no sensitivity to the strike price, time to maturity, the risk-free rate, and the volatility. I have now delta, theta, vega, and rho that is representing a unit change in the underlying asset price, time to maturity, volatility, and the interest rates. And each of these represents what's going to happen to our, approximately of course, option price. So that is, if we are long a European call option and there is a unit change in the underlying asset price, then we would expect the call option to increase by roughly 0.64. Well, let's test this out. Would you look at that? That increases by roughly 0.64. Now, why didn't it increase by precisely 0.64? Well, again, it's a linear approximation, just as we had here. We had that even though we're moving very slightly away from this initial point of interest, there is still a little bit of error. Now, this error is negligible for the interpretation and understanding that we get from implementing this Greek. One of the things that you will notice is the delta is also a nonlinear function. So we're using a linear approximation to determine what happens in this overall pricing function, but these functions themselves are also nonlinear. So it jumps from 0.64 to 0.66. So we're going to expect another change of 0.66 roughly. Now it goes to 0.67, and all of the other functions change as well. So there's a lot going on here, but at a high level, all I want you to understand is each of these Greeks represent what happens when there's a unit change in the underlying parameter. Now, of course, vega and rho having a unit change, that is a significant change. Most likely it's going to be in percentages. So there's going to be like a 0.1% increase in vol or a 0.5% increase in vol. That's going to scale down these linear approximations. But we're just going to use the underlying asset price because it's so easy to see. You can see now delta is 0.67. The option price is 11.76. What happens if the price decreases by 1? Well, we would expect that this call option price would be roughly 11.10, so 11.10, and that's exactly what we get. So all we're doing here is we're applying this idea of a linear approximation to the change in our option value to an option price via the Black-Scholes model. And that's exactly what we're doing here for each of the inputs. Remember, this is the underlying asset, this is the time to maturity, this is the volatility, and this is the interest rate. This is precisely how the Greeks work. And the upside to this sort of linear approximation is that it is linear. So if I'm trading a whole bunch of different option contracts on, say, Apple, then I'm going to have a whole bunch of different deltas. But the net delta of my portfolio, I can just sum together all of the deltas of all those option contracts, And that's going to tell me approximately how much I can expect my portfolio value to change when there's a unit change in either direction of, say, the underlying asset price or time to maturity, Vega, Rho, etc. So what this means is I get a very high level view for almost nothing of my overall option portfolio. If I am net long delta, then my portfolio value will increase when the underlying asset increases. If I'm net negative delta, then my portfolio value is going to decrease when the underlying asset increases. That's why this idea is so useful, because even if I'm trading 100 different option contracts on the same underlying, then I get a summary of what's going to happen to my portfolio value in the form of delta, theta, vega, and rho. I can just take a look at the net exposure. Now, if you wanted to take it a step further, you could even look at the second order sensitivities to see how quickly your delta's changing, how quickly your vega's changing, so on and so forth. But again, that's more of a video for another day. This is going to tell you, relatively speaking, and in kind of plain old English, what you want the market to do to make more money. So if you're net positive delta, then you want the underlying asset to keep going up. If you're net negative delta, you want that thing to keep going down because the value of your portfolio is going to increase. Now, what if you don't necessarily want to speculate? What if you're a market maker? Well, if you're a market maker, you're trying to collect this bid-ask spread, and you can argue that spreads are so tight now, there's nothing left, whatever. That's not the point of this video. You can take that elsewhere. The whole point of this video is suggesting that if you wanted to collect that bid-ask spread, then you don't want this exposure. You don't want this delta, theta, vega, rho exposure. What you do want is you want net neutral exposure. You don't want your portfolio value changing at all when there's a change in the underlying asset or time progresses or volatility changes. So what you can do then is you can try to enter offsetting positions to make your delta 0, to make your theta 0, to make your vega 0. And what that's going to do is it's going to neutralize that exposure, meaning you're going to have almost a net 0 change in your portfolio value when these variables in the market change. And then the idea is you would try to collect that bid-ask spread. So that is the idea from a market maker's perspective. That's the idea of implementing this linear approximation as a market maker. This is, again, a very crude interpretation and explanation. There's a lot of other stuff going on in that setting, but just at a high level to understand why these linear approximations are so useful in any context, whether you're managing your own option portfolio or you are a market maker, that is the high level gist of what's going on. Excuse the breach in continuity, it is quite cold out. The last thing I'd like to do is discuss this idea of a linear approximation relative to the other inputs in our function of interest. In this case, the function of interest is our Black-Scholes model, our pricing function, and we have all of these different parameters that can change. Now you'll notice if we take a look at something like delta, what happens when we change the time to maturity? Well, you can see that delta does change when the time to maturity also changes. Moreover, if the strike price changes, then our delta is going to change because that's going to affect the moneyness of our option. Now, I'm not saying the strike price will change throughout the life of the option, but when it's initially set, you can see that's going to determine our delta. The moneyness of the option is going to have an impact on that linear approximation. So what are the implications of this? Well, we also have the ability to look at second order sensitivities. That is, we don't just have to look at the change in option price relative to the underlying asset, but we can also look at the change in the underlying asset and the change in time, or the underlying asset and volatility or interest rates. So you can compute these cross partials, if you will, and you get a similar effect, and that's a second order sensitivity. What I want to do is I want to kind of give you the gist of this idea of how the parameters influence one another by taking a look at this chart. So here what we have is we have our actual theta, that is the actual change from the change in time in our option price. We have a theta approximation, and we have our initial option price here. Now what you'll notice is as we increase the time step, the theta approximation is significantly worse than the actual option price. This is exactly what we saw when we looked at this chart up here. As we get further and further away from the point of interest, the approximation is going to get worse and worse and worse. So let's bring this back down to an incremental change. And let's take a look at what happens when we change the moneyness of the option. So let's say the underlying asset starts to increase significantly. You can see the strike price is 103. The underlying, or the spot of the underlying, is 150. Now the approximation is very similar to the actual change. What happens when we actually decrement time here? Look at that. What happens when we increase the time step? The magnitude of the effect is not quite the same. So when I decrease this, you'll see, wow, that is a significant amount of error. But when we're deep in the money, it's still a reasonable approximation. So what's going on here? This is what I want to leave you with is the linear approximations themselves are assuming that we're holding all of the other parameters constant. But what you just witnessed is as the other parameters change, the effectiveness of the linear approximation itself will also change. That is, it's going to be your option price, that is, it's going to be less or more sensitive to the approximation and the error of the approximation further away from the point of interest, depending on the parameter set that you're dealing with. And that's exactly what we see here. We see the initial option price, we see the actual price in the theta approximation, and as our underlying changes, we can see, wow, this theta approximation is terrible when it's out of the money like this, or when it's deep in the money, even though we're so far away from the initial point, x0, we have a marginal error here, right? Marginal relative to this error. So all that is to say is we don't just have a linear approximation for the change in option price relative to all of the inputs, but we also have second order sensitivities. We have gamma, we have charm, we have all of these other interesting quantities that we can compute to see how all of these changes work together. I want to leave you with this idea of managing an option portfolio and the notion of hedging away your different exposures, that is the exposures that we discussed throughout this video, the Greeks. So how do you do this? Well, let's say that I have a portfolio of options and stock. As we said earlier, I'm able to add all of those different exposures from all those different contracts and equity together, and I'll have my overall portfolio delta, portfolio vega, portfolio theta, so on and so forth, right? That's going to tell me how my portfolio value will change relative to all of those inputs that we talked about, the underlying asset, the market volatility, interest rates, all of those inputs that would affect the price of the assets we're holding in this portfolio. What if I wanted to hedge away all of my vega risk, my delta risk? Well, this turns into pretty much a system of equations. What we have is we have a market where we can go out and purchase option contracts. We could sell option contracts. And our goal is going to be to find a combination of option contracts that's going to hedge away the risk that we're interested in hedging away. But moreover, when we do that, that new contract is going to bring to the table its own theta, its own delta, its own rho. And we're going to have to add that to our portfolio. So this turns into a very interesting type of optimization problem / system of equations where we're trying to figure out the best way that we can combine contracts available to us in our portfolio to hedge away the risk. Now, you can only get theta, vega, gamma, all of that exposure from option contracts. So the only way to offset it is using an option contract, right? Delta, however, you can get delta. You can either get positive delta by going long an underlying asset or negative delta going short the underlying asset from exclusively the underlying asset. That is, typically when you're trying to hedge away this portfolio risk, you start with options. So you hedge away your theta, hedge away your rho, hedge away your vega. And then once you have that combination of options that all offset, Then you can go buy and sell stock depending on your net delta position to neutralize that one last, because stock doesn't come with any vega. Stock doesn't come with any theta. And that's a very interesting component of managing an option portfolio. In a later video, I would like to actually discuss how to solve this sort of system of equations and maintain an offsetting position and talk about what rebalancing looks like. Yes, we have transaction costs. Yes, there's all of these other, actual implications when we go into the market and transact. And that's something that I would like to explore in a later video, along with these second order sensitivities, which are also very, very important as well. But until then, thank you so much for watching. I hope you enjoyed, and I will see you in the next video.